Oh no. All right. Advent of code. Day 10. You discover weather forecast. Your device suddenly turns off. Battery's dead. There's only one problem. The charging outlet in your seat produces the wrong number of jolts. Prepared, you make a list of all the joltage adapters in your bag. Each of your joltage adapters is rated for a specific output joltage. Your puzzle input. Okay, so there's no Game Boy. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating and still produce its rated output joltage. Your device has a built-in joltage rated for 3 jolts higher than your highest rated adapter in your bag. If your adapter list are 3, 9, and 6, your built-in adapter would be rated for 12. Treat the charging outlet near your seat as having an effective joltage rating of 0. Since you have some time to kill, you might as well test all of your adapters. If you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlet, the adapters, and your device? Holy moly. Ints. Let's see. What is the distribution of joltage differences between the charging outlet, the adapters, and your device? So here are these. Built-in equals ins.max plus 3. Can only connect to 1 to 3 jolts lower than its rating. In order to use every adapter, you need to choose them like this. Charging outlet has an effective rating of 0. So the only ones that can connect to it are 1, 2, or 3. Of those, you only have 1. Then you have a 4. Then you have a 5. Then a 6 or the 7. Okay. Differences equals 0, 0, 0. Jolts equals ins.sort. And then (22) differences. Okay. Def add adapters, current joltage, current jolt adapters, current diffs. Okay. Every adapter in your bag at once. Oh. Instack count. Inst times do I cur equals inst I next equals n equals int I plus 1, or built in diffs n minus cur plus equals 1 puts diffs 1 times diffs 3 times int dot each or built in. Puts cur n I int dot sort 1890. $30. Seven differences of 1 jolt. Oh. Diffs ints 0 1920. Boom. Why didn't it say what score I got? Part 2, to completely determine whether you have enough adapters, you need to figure out how many different ways they can be arranged. 1610, following arrangements. Okay. Def add adapters remaining cur remaining ways to add adapters. Return 1 if remaining dot empty. If remaining minus cur is greater than 3, return 0. C equals 0. C plus equal 1. Ways to add adapters cur plus remaining 0 remaining to C. Put ways to add adapters 0. It's um 36 ways to add adapters can't be coerced. Oh. If remaining dot count greater than 2, 274. That doesn't seem right. Total number of arrangements is 8. Oh, this is wrong. Is it? Max? And cur max minus cur is built in. Shoot. Oh. $198. Oh my gosh, I'm doing so poorly. 69. Oh, okay. Oh no, that's not good. Um, Oh. So you can either add the next one or not. RB combinations. Do n inst dot combinations n dot each do lms total equals 0. I'm doing a totally different approach. Next if inst 0 is greater than 3. Next if inst dot last plus 3 is less than built in. And times do greater than 3 equals false. Total plus equal 1 if not greater than 3 is true. If lms this is not going to work. That's way too slow. Why isn't this working? So far, plus remaining 0. Puts so far dot inspect. Puts max. Puts cur. Okay. Okay, I don't need this so far. Ins equals ins. And Oh, this is not going super well. Wow. Oh my gosh, there must be more than a trillion. I didn't even see that. Okay, great. Total number of distinct ways you can arrange the adapters. I have to like totally rethink my solution now. Why? Puts int. Okay. So we can figure out when it's a gap of more than, when the next thing is 3 away, both are required. So you have to have the 2, you have to have the 5. Array chunks equals insta unshift 0. Okay. Cur chunk equals I. If I equals pre plus 3 chunks, cur chunk, cur chunk I, cur chunk equals puts chunks inspect. Oh. Prev equals I. Oh. What? Instead, if I equals the previous value plus 3. What's insta inspect? Oh. Chunks, cur chunk, cur Ah, so they're all runs. Each do ways for chunks equals chunk ways to add adapters chunk 0 chunk dot last. Puts chunk inspect and p equals 1 ways for chunks dot each n p times equals n puts p. For that's not what I want. I want 2. Oh, wow. So bad. I did so poorly. Oh my goodness. Two minutes? Oh, oh God. That did not go well. That did not go well at all. What's up, Zrankiewicz? I'm done. It went real poorly. were all of these runs? Yeah, are there any where they're separated by 2? Interesting. Man, what was your time, Sir Ankiewicz? 4 minutes for part 2? What the heck? That is insane. Ugh. All right. Let's explain what the heck just happened. Yeah, because I wrote... Oh, okay. Dynamic programming. Fancy. Yeah, because I wrote the function that solved it. But obviously that doesn't work for how many elements you had. So then I broke it up into places where you had to stop, or where like certain elements had to be in it. And then, so that gave me like start and ends. And then for those, you could calculate how many were there. And so then you had how many ways you could, get through each run, and then you could take the product of all those. But I'm going to walk through the whole problem and walk through my very poorly done solution. All right, day 10, adapter array. A day that'll live in infamy. Patched into the aircraft's data port, you discover weather forecasts of a massive tropical storm. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Its battery is dead. You'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepared, you make a list of all the joltage adapters in your bag. Each of your joltage adapters is rated for a specific output joltage, your puzzle input. Any given adapter can take an input 1, 2, or 3 jolts lower than its rating and still produce its rated output joltage. In addition, your device has a built-in joltage adapter rated for 3 jolts higher than the highest rated adapter in your bag. If your adapter list is 3, 9, and 6, your device's built-in adapter would be rated for 12 jolts. Treat the charging outlet near your seat as having an effective joltage rating of 0. Since you have some time to kill, you might as well test all of your adapters. Wouldn't want to get to your resort and realize you can't even charge your device? If you use every adapter in your bag at once, what is the distribution of joltage differences between the charging outlet, the adapters, and your device? So that's a very confusing way of saying sort your adapters and count at a 0 at the beginning, and the highest value, add 3 more than that at the end, and then take all of the differences between them and create a distribution of those differences. So these are your voltages. You sort them. Your built-in joltage adapter would be rated 19, which is the max, plus 3, 22 jolts. Because adapters can only connect to a source 1 to 3 jolts lower than its rating, in order to use every adapter, you need to choose them like this. But why? This was confusing because I started implementing part 2 as I was reading this. Because he's like, oh, it could be 4, like you could use 5 or 6. But then in order to not skip any adapters, you have to pick 5. So then we do that. We get a bunch of differences. Same thing here. A given adapter can take an input 2 jolts lower. So you use up all your adapters, you calculate the distribution, and then you take the number of, find a chain that uses, I'm going to finish reading the problem because I didn't do that while I was doing the problem. Find a chain that uses all of your adapters to connect the charging outlet to your device's built-in adapter. Find a chain is like, there's only one chain, all of your adapters. You just sort them. To connect the charging outlet to your device's built-in adapter and count the voltage differences between the charging outlet, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? And so this is this bit. We get all of our integers. The built-in has a joltage of the max value plus 3. We sort them. This is our differences array. Because I don't have like a 0 at the start, I have to say that we have whatever the first adapter is, we have a delta of that, so we count that. And then for each pair, we increment our distribution. Ruby iterate over pairs adjacent pairs. Is this like window? Pairwise? Each cons? Oh, this doesn't exist. Each cons. So I could have used each cons here. And then, yeah, diffs.inspect. So when we do that, we get that we have 64 differences of 1 and 30 differences of 3. And so the product between the 1 and the 3 is 1920, which is the answer to part 1. Then for part 2, to completely determine whether you have enough adapters, you'll need to figure out how many different ways that they can be arranged. Each arrangement needs to connect the charging outlets to your device. The previous rules about when adapters can successfully connect still apply. The first example above with 16, 10, and 15 supports the following arrangements. Basically, like the 6 is optional, as is the 5. And some other things are optional. The charging outlet and the built-in adapter are shown in parentheses. Given the adapters, there are 8 possible ways for this first example. There are 19,208 for the second example. There are more than 1 trillion valid ways to arrange them. I did not read this line. And so I tried to just calculate it immediately. And we need to know what is the total number of distinct ways you can arrange the adapters. Let's see. No, I did terribly. Absolutely terribly. So the way I did this problem is I actually wrote the recursive function that would solve it, which is ways to add adapters. There's still day 11 through 25, which basically takes your array of values, your current joltage, your current index, and the max value. And so if you've considered all the indexes, because you're at the end, and your current joltage is within 3 of the max, then it worked. 6 a.m. Oh my god. See ya. But if the difference between your current joltage and the max is greater than 3, that is not a valid way to count them. If the next adapter is more than 3 than your current joltage, you've failed, so it'll return 0. And then you basically consider, oh, do I include this adapter or don't I include this adapter? If you do include it, your current joltage is the next joltage, and if you don't include it, you still have the same joltage, and then you return your count. The problem is that this is essentially exponential, and so it's bad and it never finishes. But what you can do is, if you look at the actual values, if you have two numbers in your array that are separated by 3, like you have 15 and you have 18 and you don't have 16 or 17, that means that you have to use adapter 15 and you have to use adapter 18. So what I do is I create these chunks of your adapter list where each chunk, the last element of one chunk is 3 less than the first element of the next chunk. So you start with 0 in your first chunk, and then for each, you go through all your numbers, and if your current number is 3 bigger than your previous one, then you're done with this chunk and you start a new chunk, and then you put that value in your current chunk and you update your previous value. So this gives us chunks that look like this. Sorry, the last element of one chunk is 3 less than the first element of the next chunk. And all these chunks are much shorter. So for these chunks, we can calculate how many ways we can use those adapters using the function that I already wrote. It requires a little finagling of the inputs, because like this assumed it started at 0, but it works, and then you just multiply those all together. Zerankiewicz says there's a dynamic programming solution, which is okay, num ways equals times inst count plus 1. Let's do 0 inst count dot each do n. Yeah, if the chunks were too big, I would have the same problem. Index equals inst count minus I. Is a Fibonacci number? Oh, 0, 0, 1, and the sum of the previous 3. Cool. Zerankiewicz, what do you study? Are you in college, or what did you study? Are you the one who threw like the cubic graph perfect matching? Are you the one who threw this at me? Yeah, what do you do? Oh, you are doing a PhD. All right. Very good. In math? You studied maths. Are you British? All right, numways. So this will be numways inst count equals 1. German. Wow. What is your PhD in? Inst count. N I. If n equals 0, if numways oops, is this right? Oh. Oh. Not if less than 3. If val mix of papers rather than just one topic, a bit of enumerative combinatorics, graph theory, and a little bit of stochastics. Wow, so enumerative combinatorics? So like the round robin problem was like right up your alley. Did I ever explain my solution? Or yeah, my solution as in like the way that I came up with to be able to generate a round robin. All right, I want to finish this dynamic programming solution. So if there's puts numways if puts num. Oh, these are ints. Nope, still no. Puts ints I minus 3, ints I minus 2, ints I minus 1, val. Minus 3. Good call. Still not working. What the heck? That's fine actually, because I do check if it's greater than 0. So there's one way to get to 0. So we start with so when I is 1, Zerankiewicz, you're the man. Oh, so close. Okay. Where's that pop? Count it. All right. Yeah, so basically the way you can compute this is you go through and you figure out how many ways you can get to 1, how many ways you can get to the first adapter, how many ways you can get to the second adapter, how many ways you can get to the third adapter. If you're looking at the nth adapter, if there are 10, basically if there's an adapter that's within 3 of you, you can use that however many ways to get to that adapter to get to your current adapter. So you check at each adapter, you check how many ways you can get to the previous 3 adapters, and you add those all up if they're within 3 of you. I think we can just do this. Yeah. Yeah. So we say that there's one way to get to the first adapter, which is the 0, because you have to use that adapter. And then you get the current value, the current voltage of the adapter. And then if there's, I'll start here. If there is a previous adapter, I minus 1 will actually always be 0, greater than 0, because you're starting at 1. If there's a previous adapter and the difference between you and that previous adapter is less than 3, then you can use all the different ways to get to that adapter to this adapter. And then same for the adapter 2 before and the adapter 3 before. And then you eventually get the number of ways to get to your last adapter. So that is that. Cool. Whew. What is it? December 10, 2020 solution. All right, that's Advent of Code, day 10. That one was a doozy.